Hey, welcome everyone. This session is a popular lecture on Ramanujan's formulae for approximations to pi. Since this is a popular lecture, we would not be doing any of the proofs or derivations, but rather we would take a look at the approaches that Ramanujan took, a sketch of the approaches that he took, the kind of steps he progressed in to arrive at the approximations to pi. Just to give you some background, Ramanujan worked on multiple areas in mathematics, specifically around analytic number theory, and this specific popular lecture is on one of the topics that he worked on, which is around the approximations to pi. So I'll present a set of slides so that you can appreciate this topic. All right, so we'll get started. So before we go into the details, I just want to get you a glimpse of the kind of formulae that Ramanujan came up with for pi. So you can see here a few very interesting formulae. So you have 1 by pi, and then you have 5 root 5 by 2 pi root 3, and so on. So as you can see, a few of these formulae are quite complex, especially the first one. It's a pretty complex formula. And then at the bottom half, you see a relatively simpler formula. But even in this formula, the kind of geometrical consideration and construction that Ramanujan had to make to come to this formula is a pretty comprehensive approach to this problem. So in fact, the two geometrical figures that you see, the first one gives you relatively less accurate approximation to pi, whereas the second diagram gives you a more accurate approximation. So in fact, the second diagram, there is a specific set of rules to be followed to construct the circles, and once you construct the circle, the kind of segments and the chords that you form inside the circle, they need to obey certain specific conditions. For example, the length QP must be equal to length MN, and AR should be equal to AS, and there are many such considerations. And then once you do that, Ramanujan says that if the circumference of a circle is so much, then the kind of accuracy that you get to pi is going to be more. So such is the kind of solution that he obtained. So this specific slide is just to show you the kind of formulae that Ramanujan came up with for pi. On the top left, you see the letter that Ramanujan wrote to Hardy in early 1913 when he introduced himself and gave an overview of his work, and then attached a few of his results so that Hardy could get interested in Ramanujan's work. And at the bottom, you see a statue of, it's actually just a bust of Ramanujan in Kolkata. So okay, we move further. So just to give a quick background of myself, I am Varaha. I'm a director of engineering at a company in Chennai called Avalara, and I am a mathematics enthusiast. I'm not a mathematician. I'm not a mathematics a PhD or a researcher, but I am an enthusiast in mathematics. I also want to take this opportunity to thank the Association of Mathematics Teachers of India, AMTI, which is present in Chennai and conducts mathematics talent search examination for the whole country. I'd also want to thank Dr. Payanivasan, who is the General Secretary of the Association of Mathematics Teachers of India, and then Mr. P. Ramesh, who is the Secretary for Popular Lectures at this association. The material to this lecture have been obtained from a few mathematical books and essays written by many mathematicians, the Borwein brothers by Bruce Brent. From the internet, we took Paramanand Singh's derivations, and then images have been taken from Institute of Mathematical Sciences Gallery and then Wikipedia. So these are the sources from which the material for this popular lecture has been drawn. So in this slide at the top left, you see one of the formulae that Ramanujan came up with, and then at the bottom left, you see a couple of very interesting puzzles that Ramanujan posed in the Journal of Indian Mathematical Sciences in 1911. The bottom ones especially aren't that complex. They're more puzzles and they can be solved with some approach. But when he posed this problem in 1911, it took a few months and nobody responded with an answer, and then Ramanujan gave the answer himself. So what this session is about, it is a non-rigorous survey of Ramanujan's formulae on approximations to pi. No derivations or full proofs will be given, and a broad outline will be provided on Ramanujan's approaches. So we are going to split this session into three. The first part would deal with the key events in Ramanujan's life, kind of a biographical excerpt. And then in part one, we'll also talk about the contributions of Ramanujan. And then in part two, we will talk about some of the prerequisite material that are essential to understand Ramanujan's approach to approximations to pi. These prerequisite material would include elliptic integrals, hypergeometric series, and modular functions. So at the top left here, you see in this slide the photograph of Ramanujan taken when he left London for India. So he was not keeping good health. He had been out of hospitals after a few months stay, so he was terribly sick at that point. And in the bottom left, you could see Ramanujan's graduation ceremony. So Ramanujan, when he left India for London in 1914, he was not a graduate. He had only completed his schooling. But owing to his original research, in 2 years he was given a bachelor's in research, and after that in another 2 years he just completed his PhD. So this photograph is taken with his colleagues, and at the extreme right you see his collaborator G.H. Hardy, who was also his doctoral advisor. So before we proceed further, I wanted to ask you, what does the name Ramanujan remind you of? Because every one of us in India would have heard of Ramanujan, and we know that he was a mathematical prodigy, and it reminds each person of different kinds of things. So some people would be reminded of the magic square, which Ramanujan had a passion to discover. So he put together many of these magic squares, third order, fourth order, fifth order, and so on. And this he did in his school days. And the second one many people would know is the Ramanujan taxi cab number, where he explained that 1729 can be expressed as sum of two different cubes. For example, 1 cube plus 12 cube, and then one more such expression. And then in that sense, he said it was the lowest such number that could be expressed as sum of two different cubes. And then later mathematicians established that you could actually write 1728 as sum of cubes of 4 different pairs and not just 2. And then you also would think of Ramanujan when you look at some of these relatively simpler formulae that he came up with. In general, Ramanujan's formulae or identities would involve infinite square roots or infinite fractions or infinite series and so on. In fact, if you look at number 4, you see that it is a continuous fraction which goes on infinitely. And then he found an approximation to that. And then there is also an interesting anecdote narrated by Mahalanobis, who was a very popular statistician and who was the chief of the planning commission that Jawaharlal Nehru set up in 1950s. So Mahalanobis was a statistician, and he was in London as a doctoral student when Ramanujan came over as a student there for his research. So when Mahalanobis posed a puzzle to Ramanujan, saying that he has been asked a question for which he doesn't have an answer. The question being that there are between 50 and 500 houses in a row, and then there is this specific house where if you take the numbers to the left and then if you take the numbers to the right, both these sides they sum up to the same value. And then he was asking, what could be the number of total houses in a row. And then within a few seconds, Ramanujan came up with a continuous series, and then he said, here's the answer, and then this answer would work for any number of houses, infinite, and it need not be just between 50 and 500 houses. And then the specific question that Ramanujan was asked, he said, was a very specific case of this much larger general series. So from these incidents, what you can infer is that Ramanujan had a passion for solving hard mathematical problems. Again, these examples are about puzzles. These don't do justice to the stature of Ramanujan, where he came up with completely new theories and concepts, and also his work generated whole new fields of study, for example, in prime number generators and partition functions and mock theta functions and so on. And his work has kept mathematicians across the world busy for the next 100 years. And it took almost a century for mathematicians to completely prove all the theorems that Ramanujan came up with. So this slide is about a brief biography of Ramanujan. This slide and the next slide would be on his life itself. So at the top left, you see the birthplace of Ramanujan in Erode. Now the street is called Arahiri Street. So this was where he was born. It was his mother's ancestor's house. And then at the bottom left, you see the house in which he lived in his school days, along with his parents. This was in Kumbakonam. And then so we have shown some of the images there. So here you have Mrs. Komala Tammal, who was his mother. Ramanujan was born in 1887, December 22nd. And then he went to school in Kumbakonam Town High School. And then in 1901, he got hold of a book called Synopsis by a mathematician called Carr. And this book was more like a handbook or manual, which had a compilation of many theorems and formulae. And because it did not have proofs, Ramanujan took it upon himself as a hobby to go through each theorem and then write proof for it and then verify what is correct or how to establish the proof of those theorems. So that was his pastime. He was spending almost all his time working through this book. And the other book that he worked on, which is not shown here, is S.L. Loney's book on plane trigonometry, which is actually a bit advanced trigonometry compared to what we do in schools, in high schools currently, because in addition to trigonometry, it also covered some of the concepts of calculus. And for a school student who was self-taught, it was quite an achievement in those days. And then in 1904, he joined the Government Arts College in Kumbakonam for something called Fellow of Arts, which is like the pre-university, which is like +2 in those days. So he joined the Fellow of Arts course, but he did not clear it because he did not pay attention to any subject other than mathematics. And then in 1909, he got married to Janaki Ammal, and Janaki Ammal outlived Ramanujan by 73 years. So Janaki Ammal passed away only in 1993, and the couple were childless. In 1910, Ramanujan came into contact with district collector, Mr. Ramachandra Rao, who gave a monthly scholarship to Ramanujan to pursue his mathematical research. And then in 1911, he started contributing to the Journal of Indian Mathematical Society, and then that's where you see a lot of his initial contributions happened. In 1912, the chief of the Madras Port Trust, he gave a recommendation to the University of Madras that the university should give some scholarship because Ramanujan was employed as a clerk in the Madras Port Office at that time. And then in 1913, Ramanujan contacted G.H. Hardy, who was the foremost number theorist, foremost mathematician on this field of number theory in that time. Just to take a pause here, one thing to note is that Ramanujan So the fact that he could educate himself is quite an achievement, and he has mentioned to some of his friends, which is quoted in the biography of Ramanujan by Robert Canigal, that many days he would forego food and just drink water because there was no food at home. And to forget hunger, he would drink water and then start solving problems in mathematics. So that was the kind of poverty that prevailed in India at that time. And Ramanujan went to London in 1914 because Hardy invited Ramanujan to come out to London to pursue his research. And then in 1914, he wrote a letter to his mother. He kept regular correspondence with his mother. And then these letters mostly were written in Tamil. And when he wrote to his friends in India, he wrote in English. And this is in 1916 when Ramanujan was conferred a bachelor's degree in mathematics through research. And then in 1918, he was recommended to be awarded a doctorate. And then in 1919, he sailed back to India. This is the Nevada ship that he sailed back in. In 1920, between 1919 and 1920, about 15 months he lived in India when he came back. But he suffered from poor health throughout, and he was moving from one place to another, expecting his health to improve. And finally, in his house in Chennai, a house by name Gomitra in Chetpet, Chennai, he passed away. And then this house was a rented house, and a philanthropist by name Nambermal Chetty in Madras at that time gave this house for Ramanujan free of rent, and then he said Ramanujan could use it without paying any money to Nambermal Chetty. So there were many great philanthropists at that time who were helping Ramanujan once they came to know that Ramanujan's work needed to be encouraged. After Ramanujan's death in 1930s, the students of G.H. Hardy, Watson and Wilson, they took over the research of Ramanujan's mathematical theorems and identities. Unfortunately, Wilson also passed away at a very early age of 40 in 1930s. And Watson, after spending about a decade on researching Ramanujan's identities, he did prove quite a few theorems, and then after that he also moved on to other fields of research. And then in 1975, this is George Andrews, who was a mathematician from the US. So he discovered that there was one notebook of Ramanujan which had many theorems. So Ramanujan had this habit of recording all his theorems and findings in a notebook. So there were two notebooks that were known to the world by 1940s, and then because Hardy was custodian of the copies of those notebooks, and the originals were in Madras at the time. And then in 1975, George Andrews accidentally discovered that there was one more notebook, and then he published the theorems mentioned in those in the third notebook. And then mathematicians after that were busy proving the theorems present in the third notebook. So between George Andrews, Bruce Brent, and Richard Askey, almost all the theorems that Ramanujan came up with were proved subsequently until the early 2000s. So it took close to 80 years to 90 years to completely prove all of Ramanujan's theorems. And then in the process, many new fields also opened up within mathematics for further research. So this is a short biography of Ramanujan. So G.H. Hardy, who was the mentor and guide for Ramanujan, said that the tragedy of Ramanujan's life was not just that he passed away early, but also that he did not have the formal guidance, so that a lot of his time would have been spent on finding new results and theories rather than having to rediscover a lot of theories. So for example, Ramanujan self-discovered many concepts and proofs and theorems that had been discovered in the past 100 years in Europe, but because the books had not been updated, Ramanujan was not aware of it, and he himself was rediscovering many of these over the course of his research. And we definitely owe a great deal of gratitude to Dr. Bruce Brent, who is a mathematician and who is 78 years old now, and he gets the credit for popularizing most of Ramanujan's theorems because he and his students proved many of his theorems. There are also a few other mathematicians who are involved in proving this. For example, the Borwein brothers took the approximations to pi that Ramanujan came up with, and then they proved all his approximations to pi theorems. And then there are also others who are involved. For example, Ken Ono, who was also who is a current researcher who is 51 years old and who is researching into Ramanujan's theorems and identities. So just to elaborate further on the greatness of Ramanujan's contributions, so we should mention that top mathematicians like Hardy and Littlewood, they all have considered Ramanujan to be one of the greatest mathematicians humanity has ever produced, on par with people like Newton, Jacobi, Euler, and Gauss. Some of the key topics that Ramanujan worked on, so it ranged from elementary algebra, and then number theory and continued fractions, which you saw, and then infinite series, which was a topic that Ramanujan was extremely passionate about, and then integral calculus, hypergeometric functions, Q series, which he developed greatly and which he used in approximations to pi and also in partition functions, and then gamma functions, theta functions, and then modular equations, and which he used heavily in his derivations of approximations to pi, and then Mach theta functions, which he discovered and then developed greatly on his deathbed, and which are present in his final letter that he wrote to G.H. Hardy, and then also in his lost notebook. And then with respect to the volume of contributions, he published in his stay about 25 research papers when he was in London for about 5 years. And then he has published in his 3 notebooks about 3,500 theorems. So here is a researcher who worked alone and who self-taught himself, and then he discovered 3,500 theorems, and then that has kept mathematicians busy over the next century. So now we'll move on to part 2. So in part 1, we covered the biographical sketch of Ramanujan. And then in part 2, we'll talk about the prerequisites to understand Ramanujan's approximations to pi. So the topics that we'll consider as prerequisites are arithmetic geometric mean, elliptic integrals, theta functions, hypergeometric series, and then the modular forms. So there are quite a few topics that Ramanujan touched upon over the course of time, and then he discovered many interesting results in that process. So at the top left, you have Bernoulli, who first researched on this geometrical structure called lemniscate, which is like a loop, and then this was in the 16th century. And then Bernoulli family has produced many mathematicians and physicists. There are 8 different Bernoullis from the same family who are all engineers or physicists or mathematics, and who are all extremely reputed for their contributions to these subjects. So we know that the arithmetic mean is for 2 numbers is a plus b by 2, and then geometric mean is square root of a and b. And then what we do is we keep deriving something called we keep deriving new numbers based on these 2. For example, we start with a and b, and then we find a plus b by 2 and square root of ab, and then we take this a plus b by 2 and square root of ab, and then we again find between them a plus b by 2 and then square root of ab, and so on. So we define a n plus 1 as a n plus b n by 2, and then b n plus 1 as square root of a n and b n. So and then what we do is we keep doing this, and then we find that the sequence a n and b n will converge to the same limit as you keep doing this this process, and then as n tends to infinity, an and bn will converge to the same limit. And then what Gauss did was he continued his experiments around this, and then he took two numbers, 1 and square root of 2, and then he found that the limit that the an and bn would converge to was related to a ratio between pi and omega. Pi we know, and then omega is defined as this quantity, and then this omega comes up in finding the perimeter of this loop. This loop is called lemniscate. So, and it has this equation to state or to give the or to define this loop. And then we know that pi equal to this quantity. So there is now a way you could relate pi and omega to the limit that the sequence an and bn would converge to. So from this slide, what we are saying is that the limit of 1 and root 2, the arithmetic geometric mean of 1 and root 2, which you denote by m of 1 comma root 2, is related to the quantity called omega. Okay, and this is the relation that you see at the end. And then there are various theorems that Gauss came up with. So here is the gentleman Gauss, and then he lived in the first half of the 19th century. So what Gauss did was he found a few relations which hold true for any number a and b, and then you try to find the arithmetic geometric mean called m. And then there are these interesting formulae. And then specifically for m of 1 plus x and 1 minus x, you have this expression. And what he also found was that you can extend this further, and then you could find this. This is a very interesting quantity, because in the same form you will find something called elliptic integrals output that would take the same form. So that's how they are all related. And then what he did further was that he took this function, and because this function doesn't change between minus x and plus x, it's an even function, and then he expressed this whole thing through a binomial theorem on the right hand side, and on the left hand side he expressed it as sum of even powers. And then he found a generic way to give the coefficient Pn. And then once you have that, you can express the AGM, arithmetic geometric mean. Yeah, so here's, he can see that 1 by arithmetic geometric mean of 1 plus x comma 1 minus x is given by this relation around this coefficient. And then we'll move on to other modes of expressing this arithmetic geometric mean. So we observed that it is expressed as relation with x, and then we change that to include theta. And then when you do that, you have another way of integrating that, and then you exclude the binomial theorem part, and then you go trigonometrically, and then you come up with this relation giving the value of this integral expressed as a relation between pi and then an infinite series to be summed. And then there also you end up with the same relation between pi and then omega related to the arithmetic geometric mean of 1 and root 2. Okay, so that was the first topic as a prerequisite, the arithmetic geometric mean. And then you have the next one is as elliptic integrals. So there are two kinds of elliptic integrals, the first kind and second kind. There are many other orders also, so, but we will deal only with the first and second order because that is what Ramanujan used. The first integral, first kind, elliptic integral of the first kind is of this form that's given here. So f of k integral of 0 to pi d theta by root of 1 minus k square sine square theta. Here phi is called the amplitude and k is called the modulus. So this modulus is where the modular form and then the modular equations come from. So k is the modulus, and then all the equations that are formed using k are called modular forms and modular equations. So this is the elliptic integral of the first kind, and then and then you can express this in something called a symmetric form using a square cos square theta and b square sine square theta. And then you have something called elliptic integral of second kind, which is a little different from the first kind. So here you don't have a denominator, and then here also you have a symmetric form, which you express as square root of a square cos square theta plus b square sine square theta. So, and then a French mathematician by name Legendre. So Legendre, so here you see his painting. There is no original photo or anything, or original or a true painting that's available. What you have here is a caricature, because that's the only thing that remains now. So what Legendre did was he put together a relation, defined something called k square and k dash square equal to 1, and then if capital K is the value of the elliptic integral of the first kind, and then capital E is the elliptic integral of the second kind, and then with k and k dash as the parameter, he found a relation among them and pi. So this gives this is a very useful relation that would find use later. So once you have the Legendre's identity, there are further things you could do. You could put k sine theta equal to sine of 2 phi minus theta, and then you have another relation expressing the elliptic integral of first kind, k of k, related to instead of k as parameter, you put something called 2 root k by 1 plus k, and then you find them to be equal. And this is for a specific case where sine 2 phi minus theta equal to k sine theta. And then we move on. We saw elliptic integrals for the first kind and second kind, and then there is a further generalization of elliptic integral called elliptic function. So where we define something called a u, which is log of secant phi and tan phi. The reason we generalize elliptic integral into an elliptic function is so that we use some of the more general forms, and you can form relations between them, which will be useful for modular equations. At the top left, you have a book written by Landon, who Landon came up with a specific identity involving elliptic functions. We don't have a painting or photograph of Landon, but the book that he wrote is still available. So he was a British mathematician. Okay, so you take the elliptic integral of the first kind, you take u, and then you define a relation called u involving involving phi, and then you put specifically sine phi as something called Sn, and then cos phi as Cn, and so on. And then when you do that, what you find is it obeys a specific set of relations. Sine of minus u comma k is Sn of minus u comma k is minus Snu of k, and so on. And then it has specific identities also, which is similar to the sine square theta and cos square theta kind of relations. And then for Landon's transformation, what he did was he put, as we saw, k sine theta equal to sine of 2 phi minus theta, and then you get tan theta out of that. And once you get that, you form a relation between Sn and Cn, and then Dn, and then you form an identity like this. And then we proceed further with the same elliptic functions, where we defined Sn, Cn, and Dn, and then we formed a relation between that and then the Snu of k. And then what we do is we define specifically relations of kn plus 1 in terms of kn. So, and then you also express kn in terms of k dash. So you keep doing that, and then you find that if you have multiple ki dash, you can form a relation between pi and then the elliptic integral k dash. And then you can also find elliptic integrals with multiple values of k dash, k1 dash, k2 dash, and so on, with each ki dash being related to its previous k by this relation. And then as n tends to infinity, you get this where limit n tends to infinity, you get it as pi by 2k dash. So at this point, you define something called q. You express this as e power minus k dash by k. Here k dash is the elliptic integral involving modulus of k dash, small k dash, and then capital K is the elliptic integral of first kind with modulus as small k. So this q, once you have it, you put it in the relation between Sn and Cn. So here you're using elliptic functions, and then you express that in terms of q, and then you find that it has some interesting relations, and you're also able to express the modulus k dash and hence the modulus small k in terms of q. So this q is one of the areas of research that Ramanujan further developed to a great extent. He called it the q series, which was one of the research areas that he handled. And then to this area, you also have a Danish mathematician, Abel, who has contributed. Abel is a name that appears more commonly in the field of modern algebra. You have abelian groups and so on, but he has also contributed in other areas, including the elliptic functions. So till this point, we have covered as prerequisites the arithmetic geometric mean. So we found that arithmetic geometric mean converges to a specific value as n tends to infinity, and then we expressed arithmetic geometric mean as related to pi and omega, and then we took elliptic integrals of first kind and second kind, and then we defined the integral values as capital K, capital E, and then we found a Legendre's identity connecting them. And we also expressed the elliptic integrals as related to pi through the Legendre's identity. And then we took something called elliptic functions as a more generalized form of elliptic integrals. And then we defined Sn, Cn, and Dn, which are similar to sine, cos. And then we found a relation expressing Sn in terms of k and k1 and so on. Once you frame the relation between phi and theta and k through Landon's transformation. And then you express different subsequent values of ki in terms of the previous values of k, and similarly for k dash. And then you find that if you put q equal to e power minus p capital K dash by capital K, you're able to express the modulus k dash or k in terms of infinite products of q itself. And you get to that through using the elliptic functions, the relations among them, Sn, Cn, and Dn, and then you arrive at this relation. So at this point, what we need to realize is all these are interrelated. You use q further in theta functions and then in modular forms. So we'll move on. So, and then what Ramanujan defined was, so these theta functions already existed, and Ramanujan looked into it and he developed it greatly. In fact, at the top left, you see his handwriting involving some of his equations, though this specifically is not related to theta function. So, Ramanujan took these theta functions of orders 2, 3, and 4, which are expressed in terms of q, and then he found some interesting relations between them, theta 4 related to theta 3, and then they both being related to theta 3 with the parameters q power 4, and then another parameter r, which is the number of ways in which you can express an integer sum of other perfect squares. And then he again went back to the arithmetic geometric mean, and then when you plug in a specific parameter e power minus pi by s, you could find some interesting relations. And then at this point, we should use something called the Poisson summation formula, which talks about a function which is increasing in one half and then decreasing in the other half, and then it has an interesting summation which can be viewed as an integral expressed like this. And then you take this and you're able to express the small q as a ratio of small k is the modulus, as you remember, as the ratio of two theta square functions. And then once you do that, you're able to express the actual elliptic integral of the first kind, capital K, using something called hypergeometric series. So you now have q, and then from q you express that as hypergeometric series. So this capital F is a shorthand notation of hypergeometric series, and in long form it looks like this. So now we have a relation through Poisson summation formula by taking some specific theta functions of orders 2, 3, and 4, expressing the relationship between the modulus k and the elliptic integral capital K through the hypergeometric series and the q series. Okay, and then if you take hypergeometric series, that also can be derived from the elliptic integral of first kind, and then the shorthand notation as expressed is, as explained before, is f. So what this means is here 1 refers to the numerator, and then 2 refers to the denominator, and then a, b, and c and then a, b, and c are the parameters that appear in the numerator and denominator. So here you can see that, as explained before, the elliptic integral of first kind can be expressed as a relation between pi and then the another hypergeometric series. So here the 2 is something that appears in the numerator, and then 1 is something that appears in the denominator. And then Ramanujan moves on to the something called modular forms. So here you have mathematician Jacobi, who was also someone who specialized in the modular forms before Ramanujan did. So what Ramanujan did was he took his own theta function. He defined his own form of theta function involving quantities a and b, and then he expressed he put specific complex numbers into as parameters a and b, and then he found some interesting relations with the theta function expressed as f of a comma b. And then he went on to define further functions, phi of q, psi of q for q series and theta functions. And then he was able to form a relation between powers of the phi function itself. Now he uses this further, we'll see that. And then what Ramanujan did was, once he had these specific forms of phi, psi, and so on, he defined something called class invariant. So what this class invariant is that you have the, as expressed here, it's capital G and small g. So once you solve the equations, the modular forms, the equations that are formed here, once you solve that, you end up with this quantity called Gn and Jn. So, and instead of solving for the individual modulus small k or the integral capital elliptic integral capital K, he found that those variables are related to some of the variables that are actually not changing. So those are called class invariants, and he called this two class invariants, G, capital G and small g, and then by plugging in the specific values mentioned here, which we saw earlier, by plugging in the specific complex numbers, we are able to find the class invariants. Now, what's interesting here is that once you have this n, you can plug in different values of n and find some interesting relations to pi. So, for example, you put n equal to 9, and then you end up with something like this. Okay, and then and if you define something, and then Ramanujan, ups the ante, and then he takes it to a different level of complexity. He defines something called p, and then he solves for p, and then he finds that pi is approximately related to this capital G of n expressed in this relation. And then he has small g with order 10, and then he finds that if you plug in this value, you find a value solvable for pi, and it comes to approximately equal to pi. And then at this point, what Ramanujan did was he put specific values of, he formed a specific polynomial equation here defined here, and then he solved for it. So once you solve for the differential equations shown in the previous page towards the end, where you have p, q, phi, and then r, and then you solve for it by plugging in the value of q and q power n, you end up with a specific generic form as described here. And then you solve for a, b, c, and d expressed as expressed based on the original parameters of small a, b, and c, d, and a, b, c, and d that you took. You find that there is a relation involving elliptic integral capital K, modulus k dash, and so on. And then at this point, what is left is to pick the accurate hypergeometric series, the specific order, because as you saw, hypergeometric series involves a, b, c, and then you have the powers n. So if you choose the correct hypergeometric series, you would be able to plug that in and solve for these variables, and you'd be able to end up with different values of pi to varying degrees of accuracy. So this was the approach that Ramanujan took. So you have the modular, just to recap, so you have the hypergeometric series, which we know. and then you have the Ramanujan theta function, which Ramanujan came up with, and then you have a whole set of identities involving phi, psi, and so on, and then you take a product of certain parameters which don't change, and you call it class invariant, and then you find a relation for that. Then you plug in different values of n, and then you end up with accurate values, or I wouldn't say accurate, with a great deal with very good approximation to values of pi. And then you get that, and then you develop it further. You form a even further general equation involving p, q, and r, and then you solve for it. And then when you solve for it, all you have to do is choose the appropriate hypergeometric series, and then you could find various relations of pi. So here Ramanujan has chosen one specific hypergeometric series involving 1, 3, and so on, and then with the specific values of a and c, and then you end up with this relation. Okay, and then if you put a different value of, let's say, k equal to root 2 minus 1, and then you define R2 as 2k, you get this value of 2 by pi. And then you have another way to approximate to 1 by pi, and so on. So basically, it's about choosing the appropriate hypergeometric series, and then the different values of R2 and then A and B, and then finding the appropriate value. Basically, it means that 1 by pi can always be approximated with the values of A, B, and then capital G of n, and then you choose the different values of A and then B and so on, and then once you plug those in, you will get the different approximations to pi. So Ramanujan took this further, and then he came up with a lot of interesting values of pi, including the very famous final identity that you see towards the end, which involves factorial 4k, and then a huge number like 26390 and so on. So what you can observe is that Ramanujan has used the concepts ranging from arithmetic geometric series, which led to elliptic integrals, elliptic functions, which led to hypergeometric series, and then you have the theta functions, and then when you do the theta functions, you also have when you do the elliptic functions, you have a quantity called q, and then you use that in the theta functions, and then when you form the modular forms, you use something called class invariance, and then you form a polynomial equation after that, and you express the solution to that polynomial equation through a combination of parameters and hypergeometric series. And then once you plug in different values of the parameters, you'll be able to find the values that will approximate pi. So this is the general path that he took. So I'm oversimplifying many of the steps here, but once you follow these steps, you can see how he has arrived at this. Now, what needs to be remembered at this point is, even though this appears like a straight path, it's actually not so, and mathematicians took quite some time. So Borwein brothers proved Ramanujan's pi formulas only in 1987. So it took nearly 70 years after Ramanujan died, and many mathematicians worked on it, and then finally Borwein brothers published it. And taking similar steps, Chudanovsky brothers, who are also American mathematicians, they developed similar formulae. You can consider those to be extensions to Ramanujan's formulae. And then once you can see that such approaches can be extended, and you can find further relations. What needs to be remembered at this point is that all of these different topics are interconnected. Nobody would have expected arithmetic geometric mean, specifically for two numbers, 1 and root 2. Once you extend that to be able to form specific relations, and then plugging in q into a theta function, and then once you find somewhat approximate values of pi, you again form a further complicated polynomial equation, and then you solve for it, and then by plugging in different values of a, b, and c, and then you find even more accurate values of pi. So these are some of the interesting approaches that Ramanujan took. So here you see Neville. Neville was a mathematician who worked along with Ramanujan. He visited Madras in 1914, and then he gave some lectures in Presidency College, Madras, and then he met with Ramanujan at the time, and then persuaded Ramanujan to travel to London to pursue his research. So these are the things that I wanted to cover in today's lecture. And just one thing to add is that a lot of these modular forms fit into something called Richard Dedekinds eta functions, and then you can understand this from that framework also. So on that note, I would like to conclude this discussion, and if you have questions, we could take those.